Every wall socket delivers a C, yet essentially zero of your devices run on it. Your phone, your laptop, your LED bulbs, all secretly run on DC. Everyone quietly translates. Here is exactly how it works. Here's the part nobody tells you. That translation isn't free. Every device you own has to convert the walls of C into the DC its chips need. And that conversion leaks energy as heat. For decades, this tax was too small to care about. Then AI arrived. Power-hungry AI chips now pull so much electricity that this quiet, invisible waste, the C to DC tax, has become the exact bottleneck data centers are scrambling to fix. Same old problem. Suddenly it's expensive. Start with the two kinds of electricity. Everything hangs on this. Picture a battery. Current flows out of it in one steady direction, from plus to minus like water down a single pipe. It doesn't change. That steady one-way flow is direct current DC. Your battery is DC. Your car battery, your phone battery, every battery, DC. Now the wall socket does something stranger. The current there doesn't flow one way. It reverses. It pushes forward, stops, pulls backward, stops, and pushes forward again. And it does this 60 times every second in North America, 50 times a second across most of the world. 60 back and forths per second. Drawn on a graph, it traces a smooth up and down curve, a sine wave. That rapid reversing is alternating current, a C. So here's the Klein split. A battery is DC, steady one direction. A wall socket is a C, reversing 60 times a second. They are two genuinely different electrical languages, not two dialects. And this raises an obvious question. If your devices all run off batteries and battery-like steady power, why on earth does the socket in your wall deliver the reversing kind instead? Why is the entire electrical grid built on a C? The answer is a fight that happened over a century ago. Here's why the grid speaks a C. It comes down to one trick DC couldn't do cheaply: changing voltage. Think of voltage as electrical pressure. To send power a long way without losing most of it as heat, you want very high pressure and a thin trickle of current. But your house needs low pressure and lots of current, or it would fry everything plugged in. So you need to crank the pressure way up to travel, then drop it way back down at the other end. A C does this almost for free with a device called a transformer. Two coils of wire sitting near each other. Because a C is constantly reversing, it naturally pushes power across that gap. It steps the voltage up or down depending on the coils. Steady DC just sits there and won't jump the gap. So with a C, you send power at hundreds of thousands of volts across the country, then step it down for your street. This is exactly what settled the war of the currents in the 1890s. Thomas Edison had bet everything on DC and built the first power stations around it. But DC in that era couldn't change voltage, so it couldn't travel. An Edison DC plant could only serve customers about a mile away before the power bled out as heat. Nikola Tesla and George Westinghouse backed a C, which could leap across whole states. A C didn't win because it was elegant. A C won because it could go the distance, and DC in the 1890s simply could not. Edison lost. So the grid became a C top to bottom, which leaves one stubborn problem waiting at the very end of the wire. Now the twist. The grid runs on a C, but almost nothing you own actually uses a C. Open up your phone, your laptop, your LED bulbs, the computer chips inside all of them, and you find the same thing. They run on DC. And there's a hard physical reason. A chip is a city of billions of microscopic switches called transistors, flipping on and off to do math. Those switches need one thing above all: a rock-steady voltage. A voltage that reverses 60 times a second would flip them into chaos. Chips demand the calm, one-direction flow of DC. So something has to translate. That's the job of the power brick, the bulky block on your laptop charger, or the smaller version buried inside your phone charger. It takes the walls reversing a C and forces it into steady DC, a process called rectifying. And here's the tell you can feel with your hand. Pick up that laptop charger after an hour of use. It's warm. That warmth is not a flaw. That warmth is the sound of the conversion happening. A slice of your electricity turning into heat instead of doing useful work. The block is bulky and warm precisely because forcing a C into DC takes real components and loses real energy every second. So every single device performs this C to DC translation quietly all day. In your home, one warm charger is nothing. But now imagine a building with 100,000 chips, each demanding steady DC, fed by a grid that only speaks a C. Suddenly, one warm brick becomes a very different problem. Here's where it gets expensive. Every time you translate a C to DC, you pay a toll in heat. One translation, small toll. But power doesn't get translated just once on its way to a chip. Follow the electricity into a data center and count the steps. A C arrives from the grid at high voltage. It gets stepped down. In many designs, it's converted to DC for backup batteries, then back to a C to travel through the building, then stepped down again, then finally rectified to DC one last time right at the server. Grid to chip, the same power can be converted 4, 5, 6 times. And every one of those steps skims off a percentage as heat. Lose a few percent here, a few percent there, and it stacks. Industry engineers estimate that by the time electricity reaches the actual chip, a meaningful slice of what came in the front door, often around 10 to 20% of total power, has vanished into conversion heat before doing a single useful calculation. Now stack a second bill on top. All that wasted heat doesn't disappear. It fills the room, and the building has to run air conditioning to haul it back out. So you pay once to waste the energy, then pay again to cool down the mess the waste created. 2 bills for one problem. For a normal office, that overhead is annoying but survivable. But data centers aren't filling with normal office computers anymore. They're filling with something that eats power on a scale the industry has never seen. And that changes the math completely. So why are data centers now tearing up decades of a C design and switching to DC? One word: chips. A modern AI chip, a GPU built for training and running AI, is a furnace. A single top-end AI accelerator can draw over a kilowatt on its own. A full rack of them can pull the power of dozens of homes. When you pack a building with tens of thousands of these, every one of those conversion tolls we counted gets multiplied by tens of thousands. A few percent wasted stops being a rounding error. It becomes megawatts of electricity and a cooling bill to match. So engineers went back to the question nobody had bothered to ask. Why convert so many times at all? What if we brought DC deep into the building and skipped the steps? That's the shift now underway. Instead of shuffling between a C and DC over and over, operators are running high-voltage DC straight through the facility. Often around 400 volts of DC, delivered as close to the racks as possible. Fewer conversions means fewer tolls, which means less heat, which means a smaller cooling bill on top. The industry is even standardizing on this. Several major chip and hardware makers are now designing racks around high-voltage DC distribution. Notice what just happened. To feed the most advanced chips ever built, the most advanced buildings on Earth are quietly doing something that sounds almost backwards. They're bringing back DC, the current that lost the war a century ago. So here's the whole picture finally clicking together. A C won the grid because with transformers it could change voltage and travel across a continent. DC in the 1890s simply couldn't. DC won the device because chips need that steady one-direction flow and nothing else will do. Between those two winners sat a messy translation, converting back and forth, bleeding a little energy as heat at every step. For 100 years, that waste was small enough to shrug off. It was the price of running one language on the grid and another inside every gadget. Nobody flipped the whole system over a warm charger. Then AI chips arrived and turned that small waste into a giant, expensive number. Megawatts lost and a cooling bill stacked on top. And the moment the waste got expensive enough, the fix became obvious. Push DC deeper into the building and cut the conversions. Which means the cutting-edge data center being built right now to feed the smartest machines we've ever made is starting to look, on the inside, more like Thomas Edison's DC vision than Nikola Tesla's a C1. The current that lost the war is quietly winning the room. So next time you plug something in, remember what's really happening in that little brick. The wall speaks one electrical language, reversing a C. Your device speaks another, steady DC. And a quiet translator sits between them, turning a sliver of your power into heat every second, on every charger in every building on the grid. It's been costing us the whole time. We just never had a reason to notice. Until now. If your device runs on DC but the grid runs on a C, the next question is obvious. Where do batteries fit, and why is the whole world now racing to store DC power at grid scale? That mechanism is next.